Now that we've talked about different key features of a polynomial, we'll try to write the equation of the polynomial from the graph. Something we just reviewed was that if we know a root of that polynomial, then we can also describe one of the factors of that polynomial. So if x equals c is a root, then x minus c is a factor. So we're going to start by looking for roots that are in the polynomial. We've also talked about multiplicities. So when I find these roots or zeros, I'm looking at the x-axis, seeing those x-intercepts. So there's one at -5. There's also one at -1 and at +3. If we think about the multiplicities that are going on, here at -5, we have a bounce off the x-axis. That's going to make this have a multiplicity of 2. The -1 is going straight through -1, and at +3 we're bouncing again. So we have another multiplicity, so that's multiplicity 2 as well. Each of those roots has a factor associated with it. So we're going to create the factors like x plus 5, x plus 1, and x minus 3. Because there are multiplicities, we have to include those. So it's x plus 5 squared, x minus 3 squared. And there could also be some type of vertical stretch or vertical shrink that's going on. So we're going to put that little a in front so that it is the scalar of whatever factor that might be. To find that value, we can plug in a point on the graph, and I'm going to use the y-intercept for right now because this is an x-y coordinate. We know that when y is 2, x is 0. And if I plug in 0 for all the x's, 2 for the y, we can solve for our unknown a in this problem. And we're going to just work this out algebraically. So 0 plus 5 squared is going to be 25. 0 plus 1 is just 1. And -3 squared is +9. So we have 9 times 25 to work with. 9 times 25 is, let's see, 200, 225. So if I divide by 225, we get a equals 2 over 225. And it doesn't have to be a nice number. It could be a really small decimal. It could just also stay this fraction since that won't reduce any. But we can now say that the actual polynomial is 2 over 225 x plus 5 squared, x plus 1, and x minus 3 squared. So the main ways that we're going to write the equation of a polynomial is looking for those x-intercepts and thinking about their multiplicities. In this second example here, we have an x-intercept at -2, and we see it bounces. We have an x-intercept at +1, but it's doing that wiggle or that bend in this. This is a multiplicity of 3 because it's got that cubic-like behavior. Then we have a third x-intercept at 3, and it's going straight through them. So if I was creating the equation of this, I could take this x-intercept, x equals -2, and make the factor x plus 2. Since it is bouncing, it has a multiplicity of 2, I'll make a squared. We have an x minus 1 coming from this root, x equals 1, but it's going to be cubed since it has that cubic multiplicity there. And then lastly, we have x minus 3 with just an exponent of 1. We're going to think about what that leading scale, whatever that vertical stretch or vertical shrink might be. And we can plug in any point. It doesn't have to be the y-intercept. If we can easily see the y-intercept, we can use that one. But we can also use any other point. So I know when x is 2, y is 16. If we take this to plug in, we can simplify and solve for a. So 2 plus 2 squared, so that's 4 squared, which is 16. 2 minus 1 is just 1, and 1 cubed is still 1. 2 minus 3 is negative 1. So we end up with 16 times 1 times negative 1, which is just negative 16. So I would write that as negative 16a. Solving for a, we get negative 1. So now y equals, you can write negative 1 x plus 2 squared, x minus 1 cubed, and x minus 3. You don't have to write the 1 necessarily. Sometimes we just write negative and then x plus 2 squared and so on. If you want to pause the video, you can go ahead and try this one on your own. If you've already tried it, that's awesome. If you just want to follow along, that's okay too. So I've got x equals 1. That's bouncing off the x-axis. So that's a multiplicity. That's a multiplicity of 2. Then we have another one at x equals 3. And it's going straight through it. So there are really only 2 x-intercepts to deal with. But this one's counting twice since it's a multiplicity of 2. I get x minus 1 squared for the factor from this x-intercept, and a factor of x minus 3. There's the unknown vertical stretch or vertical shrink that could be happening. It could be a reflection, we don't know. So in the last one we saw a negative, that was a reflection. It didn't really stretch it. But I'm going to plug in some other point, and we've got a point 2, 1. So when x is 2, y is 1. There's our x and y coordinate. Now that we've got our x's and y's, the only unknown is a, and now we can solve for a. So 2 minus 1 is 1, 1 squared is 1, 2 minus negative 3, or 2 minus 3 is negative 1. So we end up with 1 equals negative 1a. So a is negative 1. And our final equation would be negative x minus 1 squared, x minus 3. You can write a negative 1 there, or just leave that as a negative. If it's not from a graph, it might be from some type of written description. These are asking us specifically to write them with real coefficients. And we will see some in another video that talk about complex coefficients. So that would be things like with I in them. Let's just focus on real coefficients and real roots right now. So we have roots at -5, 0, and 3. If we want to write them out like we were doing the other ones, we had x equals -5, x equals 0, x equals 3. And from there, we would write our polynomial factors. So x plus 5. X minus 0 doesn't really have anything, it's just x. Oftentimes, because it's just x, we write that first. But the order doesn't matter really. What is important is that we can see that it is all being multiplied, and we have this constant unknown factor that could be vertically stretching or vertically shrinking it. The other information they're giving us is that f of 1 equals -36. That is the same thing as when x equals 1, y equals negative 36. It's a different way to convey that there's a point on that graph at 1, negative 36. So if I fill in what we do know, then we can start simplifying things. Remember, there were no multiplicities that were stated in this one. So 1 plus 5 is going to be 6 times 1 times negative 2 so that's negative 12a. Dividing by negative 12 gives me positive 3. So the actual polynomial, I guess f of x, not p of x, would have a coefficient of 3. I'm going to write that x in front first so that it's not as awkward here in the middle. And then we've got x plus 5 and x minus 3. It does specify that this is a degree 3 polynomial, so when we think about it, there were 3 roots, so it is degree 3 as well. The next one, we have a little bit more complicated zeros here. So if we have a 0 at 3/4, we had previously talked about how would I solve that. So I'm going to write that x equals 3/4. To get the to get the factor, we would solve for this backwards to get it back equal to 0. So I can multiply that 4 back over and then subtract the 3 and get 4x minus 3. What we do not want to do is just say, oh, subtract the 3/4 over and make that x minus 3/4. There's another x-intercept at 1/2. So I can multiply that 2 over and get that 2x equals 1. Subtract the 1, that makes 2x minus 1 equals 0. We had one at negative 4. So we've already dealt with these. X plus 4 equals 0. And x equals 3. Subtract that 3 over, x minus 3 equals 0. These are the factors. Now, we do have some multiplicities going on in this problem. We've got the roots at 3 and negative 4 have multiplicity of 2. So when we create our equation, we're going to need to make sure that we are including those multiplicities. So I'm going to start writing this in factored form. On that x plus 4, I'm going to make it multiplicity 2, so it's squared. The x minus 3 is also squared. We have an unknown scalar, some type of vertical stretch or shrink. And now we use the other information we have. So they gave us another thing. This is actually the y-intercept at 0, 12. So when x is 0, y is 12. We'll still do all the simplifying algebra for this. So 4 times 0 minus 3. 2 times 0 minus 1. 0 plus 4 squared. 0 minus 3 squared. If I did 4 times 0, that's just 0, and 0 minus 3 is negative 3. 2 times 0 is 0. 0 minus 1 is negative 1. 0 plus 4 is 4. 4 squared is 16. 0 minus 3 is negative 3, but negative 3 squared is 9. And if we need to use a calculator, that's fine too. So we have negative 3 times negative 1 times 16 times 9. So 432a. So a is whatever 12 divided by 432 is. Now we do want to simplify that. So 12 divided by 432 gives me this decimal. If I make that back into a fraction, I get 1 over 36. So the function is going to be 1 over 36 times 4x minus 3 times 2x minus 1 times x plus 4 squared and times x minus 3 squared. If we were thinking about the degree of this one, you've got 1, 2, 3, 4, 5, 6, so it's a degree 6.